So we have talked about how you can write a macro in the macro window and then also run it from the macro window with the play button. There's other ways to run macros, and one of them is using a directive. So we have actually two directives. We have the $RunMacroAfter Directive and then also the $RunMacroBefore Directive. And these are really handy when the macro that you've written is one that you'd like to play immediately before you do some calculations with the EES or immediately after you do those calculations. So for example, maybe you want to load some data and then use your EES program to manipulate that data. That would be a situation where you might want to run a $MacroBefore directive. Or maybe the results of your calculation are something you'd like to save or something you'd like to plot. In that case, maybe you want to write a $RunMacroAfter directive, right? And these are directives, so you put them right in the equations window. You can either call the macro by name, so if you've written a macro in the macro window and saved it with your EES file, or you've written a macro as an EMF file and saved it somewhere else, you can write $RunMacroAfter and then just put the macro name, and it'll go run the commands that are stored in that macro. Or if you'd like, you can just put the macro commands right into the equations window immediately after the $RunMacroAfter directive, and then before the $endMacro keyword, right? So you put your macro commands right there in the equations window, and they would be run in this case after the calculation was completed. If you wanted to do the same thing for $RunMacroBefore, it looks exactly the same. It's just that this macro is run before the calculations are completed. All right, so let's do a real simple example to illustrate this. And what we're going to do is quickly build a EES program that simulates a periodically driven second order system. So here's the ODE, the differential equation. It's a mass spring damper system, and the forcing function is a cosine. And we can solve this pretty easily using the numerical integration capabilities of EES. So we'll do that here in a second. But then where we get to practice with the $RunMacro, in this case $RunMacroAfter directive, will be that once we have run a simulation, it'd be really nice if I could just automatically look at a plot that shows the results of that simulation, so that each time I change something, a new plot will be built, and I can just look at what is the impact of changing the parameters on the solution. So to simulate the system, the first thing I got to do is come up with the state variables and get their state equations, so their derivatives. So in this case, this is a pretty, I guess, classic example where the state variables are going to be position, y, and velocity. And so I need the derivative of y and v in terms of the state variables themselves and time. So dy dt is easy. Dy dt is just velocity. And then dv dt I get from the governing differential equation here. If I just solve for the acceleration, which is dv dt, I see dv dt here is 1 over m times the forcing function minus the damping force minus the spring force. So I'll go ahead and program these in EES. I'm going to start by setting the unit system. So I'm going to use radians. I have a trigonometric function, so I better set either degrees or radians. I'm going to set radians. I'll go ahead and set some values of these parameters. So let's do 1 kilogram. Let's start with undamped. So B is 0, and then K is 5 newtons per meter. F naught is 20 newtons, so that's the amplitude of my forcing function, and then we will apply that at a frequency of 10 radians per second. So omega is 10 radians per second. Okay, and then what I have to do next is program my state equations. So I have dy dt is equal to v, and I have dv dt is equal to my forcing function, so F naught cosine omega t, minus the damping force, bv, minus k times y, the spring force, and that whole thing divided by m. Alright, so I have to decide how long I want to simulate for. So let's simulate for let's see, 60 pi divided by omega, right? So that's something like, I guess, 30 cycles of the forcing function. And now I want to actually just integrate these two state equations through time, and so here we'll just use the integral command. So v is the integral of dv dt with respect to t from 0 to my simulation time, and y is the integral of dy dt with respect to t from 0 to the simulation time. And if you're not familiar with the integral command, there's other videos that you should go look at that will help you with this really pretty handy capability and ease. So if I run this, I'll get v and y at the end of the simulation, which isn't really what I want. If I want to make a plot, I'd like to get v and y as a function of t, so I need to add an integral table. So I will use a $integral table directive here, and the integration variable is t, and then the things I'd like to put into the table are y and v. And if I run it now, I can see this is a column for t, and then for every value of t I have y and I have v. And the way this is set up now, it's using the default integration parameters with some default accuracy, and it is showing in this table every single step that it took to try to get that accuracy. And there's ways to change all of that, but that's not what this is about. So here's my solution, and what I'd like to do next then is actually plot this solution automatically every single time that the calculations run. So basically I'm going to get a new plot that will let me immediately see the results of changing the parameters or whatever it is that I want to do. So I'm going to open a macro window here. So open the macro window, and again I can do this in a few ways, but what I think I'm going to do is just try to record the commands that I would do by hand, and then that'll get me close. And if I need to modify those commands, I can just down here in the macro window go in and modify those to do kind of what I want. Okay, so I think the first thing I want to do is make a plot. So I'll go here to, well, the first thing I want to do is set recording to on. So record macro commands, and you can see here it says that I'm recording my commands. So I'll go to plots, new plot window, and let's plot y as a function of t, and that seems okay. So we'll hit OK, and you can see here kind of the interesting beat phenomena that you get when you do this. And then down here you can see the macro command that was recorded. So let's stop recording for a second and go here and look at it. I think it looks okay. One thing I probably want to be careful of is that as I change things, there may be more or less than 2200 rows. So here it said rows 1 to 2200. If I just get rid of this, I think it'll just plot all of the rows. So that seems good. The other thing that I might want to do is make sure that the Y scale here is the same, even as I change things that might make the plot get bigger or smaller, so that I can actually compare between them. So I'm going to go back here for a second, and again set recording to on, and then I'll go to here and right click on this, and yeah, I'll do maybe minus 0.7 to 0.7 with an interval of 0.2, and I don't know, grid lines seem okay, and hit OK. And now I go in here and turn off recording, and I can look at this again, right? So Y here, this is only ever going to change the name, the scale of plot 1, so the first plot, whereas what I'd really like to do is change the scale of whatever plot I just did, right? So I think the way you do that is you put instead of plot 1, you put a 0 there, which says change it for the foremost plot. The rest of this stuff is probably okay. I don't really care. The last thing I'd like to do is bring up the plot window so I can look at it. So I think that's just show window. macro command, and if you didn't know that, you could go look in the macro command information dialog and plots. And I think that's it. If I go back here, then what I'd like to do is play this macro every single time I run my calculations. And so that's a $run macro. In this case, it'll be after. And I can do this one of two ways, right? I can either just say play macro 1, which is this macro I just made, or if I wanted to, I could actually take these commands and shove them up here and then put them between a $RunMacroAfter and a $end macro keyword. But I don't see the advantage of doing that, so we'll just do it this way. And now I think every time I run my EES program, so let's just run this again, calculate solve, hit OK, it should go ahead and make for me a plot, and you can see that's what it did here. If I don't want to overwrite the last plot I did, what I could do is just take this out, in which case it'll just make a new plot, which probably is more like what I want, because I want to be able to compare the new plot to the old plot. So let's see what happens if I add a little damping to this plot. So maybe point, I don't know, 2 might be a reasonable number, and we'll just run that and hit OK. And what it should do now is make another plot. And you can see the nice thing is that I can go back to the first plot. That's what it looks like without damping. This is what it looks like when I add damping, right? So I don't have to go through all the keystrokes of making a plot. You know, I could put this back to 0 and maybe change this from 1 to, I don't know, let's change it to 0.5 and see what happens. Run that. And I should get a new plot. And yeah, it's interesting. As the natural frequency gets bigger, you can see the amplitude gets larger. You know, I can go back to the original one to see kind of what happened. But yeah, that's the power of the $RunMacroAfter. Is you know, I don't have to go through all those keystrokes. It just is done for me in a macro every single time I run my calculations.